JPEG image compression. In last session, we discussed about the video compression, right? In video compression, I stopped a specific point. I told you it is very similar to the JPEG image compression as well, right? We can start from that point onwards. Uh, Before that, just see what are the image types that are available in our computer systems, right? There are a bunch of image types available in our computer system. The first one is JPEG, JPEG or JPEG, PNG, GIF, SVG, PSD, PDF, BMP, EPS, TIFF, TIFF, right? Those are some examples of image types. Do you know, are there any difference in those image types? Or how about the idea? Those image types are very similar to each other or having some different properties. How about your idea about this? We have a bunch of image types. Are they similar or not?
No.
No, right? We have specific properties of each other, right? There are some specific properties that are available in JPG in with compared to PNG. PNG has some good properties with compared to JPG and so on, right? Then let's take one by one and see what are the main properties, right? I'm not taking too much time to explain these things, right? These are very easy actually, right? Therefore, I'm not taking too much time to explain the image types and properties of image types. I will briefly explain. Then you can go through this note and get a better idea, right? Okay, first, there are two types of images. These are the image types, right? Or the file extensions. But we can categorize these image types into two main components. First one is vector and raster. Second one is raster, right? Raster images are completely made by using the pixels, right? 2D grid. We can create a raster image by using a combination of pixels. Let's say it is a 64-bit image. It means it has 64 pixels, right? And each and every pixel, it has a unique value, right? For a black color, the value should be 0. For a white color, value should be 255 if it is a 8-bit image, right? Then JPEG, GIF, and PNG are some examples of raster images, right? Raster images are made by using sequencer, the collection of pixels. The disadvantage of raster images are when you zoom into more and more into this image, you can from a specific point, you can identify the pixels without the actual image, right? It is the disadvantage of raster images, right? I'll show an example. In this image, this is a JPEG image, JPG image, right? When I zoom into this image, you can see some point onwards it will getting blurred, right? You cannot clearly identify the margins of these objects. See, these are some distorted areas, right? Colors are blurred, right? See, this is the disadvantage of raster images. See, in this area, we can see the pixels, right? Some square shapes areas, right? Right. This is the disadvantage of using this raster images, right? But it has some properties, some editing tools. We have to use the raster images, especially in Photoshop, right? Okay, then finally, you can come up with the definition. Raster images are made by combination of pixels, right? If you find an image in online platform, it will definitely in pixel format or raster format. Next type of image is vector. Vector images are created by using a, it's again created by using the pixels, but pixel value will be calculated by using the formula, right? Raster images are made by using pixel. We can see the image by using pixels, but the pixel values will be changed according to the zoom in and zoom out operations. The pixel value will be generated by using a formula, specific formula, right? Then once you zoom in or zoom out, we cannot identify any color change or any boundary changes, or we cannot see the pixel when you zoom into more and more into the image, right? This is the advantage of raster vector images is the colors or the pixel values will be calculated or generated by using a specific formula, right? That is the difference in between vector images and raster images. Raster images are made by using a combination of pixels. Vector images are using vector images are created by using a specific kind of formula, right? In ESP, EPS, and AI, Adobe Illustrator, and PDF are perfect some examples of vector images, right? Uh, in graphics industry, let's say you are going to create a logo for a specific company, right? In this company, they have to use this logo in everywhere. Let's say they are going to create a letterhead. They are placing their logo on top of the letterhead or the page. In some cases, they have to uh, print a large scale banner, right? Then again, they have to use their logo, right? But if we use a raster type image as for the logo, it is good for small scale printouts or in for some letterheads. But the raster images are not suitable for banner printing like large scale productions, right? Therefore, the vector images are more suitable for logo design, right? These are the main difference of vector and raster images, right? Then is another topic related to image resolution, high resolution and low resolution. In other words, we can see this is the quality. This topic will be talking about the quality of the image, right? We can measure the resolution or the quality of the image by using two parameters. First one is DPI. Second one is PPI. DPI means dots per inch, right? PPI means pixel per inch. Uh, Frequently, dots per inch unit is frequently using in printing purposes. Pixel per image, that unit will be mainly using in displays, right? When we discussing about the displays and other digital technologies, we are using the measure PPI, pixels per inch. DPI is mainly using printing purposes, right? What is the meaning of dots per inch? Dots per inch means how many dots that are printed in a inch, right? Measure of the number of dots that are available in a single inch, right? When we increase the dots per inch, the quality of our print will be increased, right? Quality of the image will be increased. And same as the pixels per inch, number of pixels that are available in a single or each and every inch will be, let's say, increase the number of pixels, the quality of the image will be increased. Then the number of pixels will be decreased, the quality of the image will be decreased, right? DPI and PPI both are some measure of the quality of the image, right? Then for websites, the standard quality of the image or resolution of the image is 72 dpi, 72 dots per inch. What is the reason? In websites, when you load a specific website, it should download all the images, available images from the server to your browser, right? If the images will take high uh, file capacity or high resolution, it will take too much data, and as well as it will take too much time to load your page. It is it is a disadvantage, right? Okay, DPI means dots per inch. When you increase the number of dots per inch, the quality of the image will be increased, right? Uh, PPI means pixel per inch. When you increase the pixels, number of pixels of an inch, the quality of the image will be increased, right? In another side, when you decrease the number of dots per inch or pixels per inch, it will decrease the quality of the image, right? I hope you understood that concept, right? Okay, then the most suitable quality or resolution for a website web display image is 72 dots per inch, right? But in printing purposes, 300 dots per inch is the most suitable one. The recommended one is 300 dots per inch, right? See this example, this one. You can see 100 dots per inch for the first image, 200 dots per inch for the second image, 400 dots per inch in the third image, right? What is the most good one? You can see this design, L-shaped design is perfectly in the third image with compared to first one, right? We cannot identify a good quality image, good difference or good design in the first one, but we can identify a good design in third one, right? Same area, right? See, this guy same in all three pictures, all three images, but see the difference. This one, this blue color is represented by using only just one pixel or one square. But in this case, it use four squares. In this case, it use 16 squares. Then this one will be given a good quality of this image, right? In this image also, this is very low resolution. Then we cannot identify the borders, boundaries of this image, right? We cannot identify the color difference. We cannot identify the sharp edge boundaries, right? When you increase the number of pixels or number of dots per inch, it will give a high quality image. In other words, it will give the sharp edges, very sharp colors, and very good quality, right? This is the difference of high resolution and low resolution. Then these are the examples of image types. JPEG or JPG, both are very similar. PNG, GIF, TIFF, PSD, PDF, EPS, AI, Adobe Illustrator document, Adobe InDesign document, and raw image format. Let's take one by one and see the main properties. JPEG and JPG are both similar. Then why we use four letters in this one? Why we use two letters in this one? JPG, JPEG. What is the difference of this one? Why we using JPG and JPEG? Both are very similar. The reason is in previous operating system, it only allows 3 characters for the file extension, right? Let's say for the image, we each and every image we have some extensions. See, uh, see, this is the extension JPG, PNG, TIFF. These are the extensions. In previous scenarios, For previous operating systems, it only allows 3 letters for file extension, right? But in nowadays, it allows 4 letters. Therefore, we can add JPEG or JPG both for the JPEG image type, right? And we can consider this JPEG image format is a lossy compression. What is mean? Lossy compression means once you compress a JPEG image, it will reduce the quality. It will definitely reduce the quality, decrease the quality as well as the file size, right? When you compress the JPEG image, it will definitely make some small tiny errors, small tiny changes with compared to original one and the compressed one, right? The meaning of lossy means lost some information. When you compress JPEG image, it will definitely lose some amount of information, right? That is why we called lossy compression. And another difference or another property of JPEG is for a JPEG image, it has a image background, right? When you download an image from internet, definitely there should be an image background. Let's say there is no things to display in the background. It will add some white pixels around the object. For an example, let's say see this image. This is an image of apple, right? This is the object, but there is no let's take this example. This one is better. This is the object. There's no nothing to display in the background. Then this background will be filled with some white pixels, right? This is the this is a JPEG image, right? Okay, these are the main properties. First one is it will perform lossy compression. It means lost some information when you compress JPEG image. Another property is always JPEG image has a background pixels, right? When we go to the PNG, portable network graphics, this one is most used in uh, uh, image transmission, right? When you send an image from one place to another place, we are using PNG, as well as PNG file types are lossless file type. What it means, when you compress the PNG file types, it will not lose the quality, right? Still, if you compress this one, the file type will be reduced, but the quality will be not changed, right? That is the meaning of lossless. And another difference in between JPEG and PNG is PNG images are not having a background. Let me show you an example. When I get a PNG image, see this example. This is the object. Then we have a transparent background for a PNG image, right? When you load this image in the Photoshop or any other editor, you cannot see a background pixel. It will be transparent, right? Right. This is the main difference in between JPEG and PNG, right? Then GIF. GIF are mean by graphics interchange format, right? Graphic interchange format. It is formed from up to 256 colors, RGB color space using, right? It is a another type of image, but we can see some animation, right? This GIF image contains some kind of image layers, right? Set of images, and uh, the images will be changed with the time. I will show you an example. This is an example for GIF image. This one. See, the set of images are changing with the time. Then we can see some animation. These images are changing continuously time to time, right? Then we can see some animation. This is the file type of GIF, right? Uh, right. GIF image types mainly we can find in social media platforms, Facebook, Instagram, like platforms, and also in web pages. We can see many number of GIF images, right? These images are animated with time, with respect to time. Then it will change the frame by frame of the image, and we can see some kind of animation, right? Okay. Then TIFF. TIFF is a last file type, and TIFF means tagged image file. It is another raster type image type, right? Raster image type, and it has lot of quality, right? The quality is very high. Then the file type should be very large, right? This TIFF file type is mainly used in printing purposes. Photographs and some banner printing, we are using TIFF because the file type, the quality of the image is very high. Then the file type, file size again high, right? Then this is a lossless compression. If we perform some kind of compression algorithm on top of this TIFF image, the information not going to be lost. Then we call TIFF image type is a lossless image type or the file type. Then PSD, Photoshop document. When you create a Photoshop document, Photoshop project, the file will be saved in PSD form, right? This file contains layers, right? When you add the things to the project, these things will be added as some layers. I will show you an example. I will add this one as the first layer, right? Then if I add this one on top of this one, this image, you can see this one. See, these layers will be added layer by layer, right? When I add some text on top of this one, something like this, again this text will be added as another layer. When I add another image to this one, let's say the second one, this one here, this image is added as another layer for this project, right? When I save this one will be saved as a as a PSD file format, and this file type has some kind of layers, right? Then we can make some modifications layer by layer, right? If I want to change some changes to this layer, then I can add the required changes. Let's say the font size, right? Font size and the spaces in between letters. If I add these changes, it will only add it to the selected layer. It will not affect it to another layers, right? Then let's say if you want to uh, change the opacity of this, just only this layer, then I can select this layer and change the opacity. See, changes will be only affected to the selected layer, right? This is the main difference of PSD file format, right? Then PDF. All of you have used this file format. This is mean by PDF is portable document format. It means you can share a PDF document and you can open it anywhere on any platform without using a specific software, right? Let's say it is Adobe Photoshop or PSD file. If you send PSD file from some place to another place, then you are going to open it from another computer. There should be definitely there should be Photoshop installed in the second system, right? Without Photoshop, we cannot open these PSD files. But in PDF portable document format, we can open it anywhere on any computer, right? Without using a specific kind of software, right? That is the main advantage of PDF file type, right? Then EPS again, it is very similar to PDF, right? This one is a vector format. PDF is a raster format and this one is a vector format, and it contains high resolution graphics to print something, right? And this one also we call this one as universal file type. Universal file types. The reason is there is no need a specific software to open this type of EPS files, right? For some kind of high resolution graphics purposes, we can use EPS file types. Then Adobe Illustrator document. This one is also created by using the Adobe Illustrator software. And this one is again a vector file type. And this one is mainly used in logo design, like graphic design things, right? And Adobe InDesign document, this software, Adobe InDesign is mainly used in creating some publications like newspapers, magazines, ebooks, and so like related things. Then the advantage of this software is we can add Photoshop files as well as Illustrator files, and we can combine those things and create a single product, right? Let's say you are going to design a newspaper, then you have to add some edited photos. Then you have to add some logo type text or logos to a single document. Then you can use Adobe InDesign software, right? It allows us to add Adobe Photoshop as well as Illustrator files, and we can combine those things and create a single product. All right. Then this is a bit different, raw image format. These raw image formats are mainly generated by using some cameras, right? In cameras, let's say if it is a digital camera, right? When you take a photograph, it will add all the uh, elements, all the details to that file without processing, right? Without editing, without changing the color, without changing the color quality, it will add all the information, all the details to the single file. Then the file type is increased, right? Definitely, the digital camera, high quality camera, the create a file is created by using a high quality camera. The file size should be very high, right? When you process on this raw files, we can reduce the file size and we can increase the information, the colors and other things. We can increase the quality of the image. Before processing, we call it as raw image, right? There are 4 types of raw images: CR2, CRW, NEF, and PEF. Mainly, as I correct, CR2 and CRW profiles are made by using Canon cameras, right? Canon cameras. Then NEF files are mainly used in Nikon cameras, right? In Nikon cameras, NEF files, raw files are generated. Then PEF files are generated by using Pentax, I think I'm correct. Pentax digital cameras. PEF file types are generated by using Pentax digital cameras, right? CR2 and CRW files are created in Canon cameras. Nikon cameras, NEF file type, raw file type is created. Then PEF files, uh, Pentax digital cameras are created. PEF file types, right? Okay, then we can come to the JPEG image compression. It was established in 1986, and still these compression algorithms are using, right? This is very standard image compression method, right? Uh, then it is approved by ISO and ITU organizations as well, right? Let's go about this topic, into this topic. See, in first image, we can see the original image, 100% quality image. When you compress more and more to the same image, we can see some distorting is there. See, the colors are changed, then the boundaries are very distorted boundaries. We cannot identify the sharp boundaries. In original one, we can identify these boundaries very sharply, right? Very clearly, we can differentiate background with this foreground, this object, right? When you perform more and more compression on this image, we cannot clearly identify the boundaries, right? And also the colors are changed. Then we can see some amount of pixels are there. In this first image, we cannot identify the pixels, right? Pixels and these boundaries very clearly. But in this case, we can identify this. See, this image also, we can see some pixels. See, this one also, it will give some very distorted boundaries. See, right? When you add, when you perform compression more and more on a image, the file size is decreasing, as well as the quality of the image will be decreased. Then we should consider both. We have to compress the size, and we have to make sure the quality is not changing too much, right? And I forgot to show you an example. See, these three images are same, very same, right? Same content. But let's see the file size. This is JPG image. This is PNG image. This is TIFF image. See, in JPG image, 99.7 kilobytes. But in this case, same content, same quality type image, it has 500 kilobytes, right? Then TIFF, for the TIFF image, 1.07 megabytes. I told you earlier, TIFF is mainly used in printing purposes. It is high quality image, right? You can see the file, same content, but the files sizes will be changed according to the file extension, right? When we go to the details of all of three images, see, this is 72 dots per inch for JPEG. PNG, 850 pixels per inch, right? In the TIFF, uh, resolution is 72 dots per inch, but see the quality or the file size will be uh, getting high with compared to other two types, right? Okay. This is the pipeline of JPEG image compression. Up to this point, we discussed in video compression as well. After finding a frames, we are converting the color space from RGB to YCB CR. After this point onwards, all the steps are very common for image compression and video compression for in both compression algorithms, right? First, we are applying DCT, right? DCT algorithms or discrete cosine transformation. After that, quantization, then zigzag scan, then DPCA, in other words, differential pulse code modulation. Then runner length encoding is applied. Then finally, we feed the result into entropy coding, in other words, Huffman encoding. Then finally, we can come up with the compressed JPEG image, right? Let's discuss these steps one by one. Right. This is the summary. First, transform RGB to YCB CR and subsample colors or downsampling. Then perform DCT on the image blocks. Right. We are finding blocks 8 by 8 blocks and perform DCT or discrete cosine transformation. Then apply quantization. Then perform zigzag ordering, runner length encoding, and DPCM. Right? DPCM means differential pulse code modulation. Then finally, we can perform entropy coding or Huffman coding for more compression. Okay, let's take this step one by one. You know what is the purpose of changing RGB to ICBCR, because human eyes are more sensitive with the Y part, Y component, or the luminance part, or the brightness part. Then we are separate color part with the luminance part. And in the RGB, we will only consider the colors, red, green, and blue color spaces. But in YCBCR color space, Y component is only carried about the luminance or the brightness of the image. Then CB and CB or CR color spaces or color channels are carry about the color information, right? That is the purpose of separating the color information and the luminance information. Then downsampling, right? We are taking CB and CR components separately and Y components separately and perform some downsampling. I have explained this one in this slide as well in the video compression, right? You can see first take the luma part and chroma part, then chroma part will be reduced and finally come up with the luma plus chroma. This is the downsampling or subsampling, right? When you see this notation, this notation 4 by 1 by 1 means we are getting 4 Y component, 4 pixels for Y information, 1 pixel for U information, 1 pixel for another V information. That is the meaning of this notation, right? We are getting 4 pixels about the information of luminance, 1 pixels from chrominance and or the U component or CB component, and another one for V component or CB component, sorry, CR component, right? The notation of this one. In this example, see 422 means 4 luminance information. See 4 luminance information for a specific punch, 2 chrominance information, and another 2 for CB or and CR information, right? This notation is representing the amount of information that are carried with Y, U, and V channels, right? Then discrete cosine transformation. So this one, using this discrete cosine transformation, we are taking uh, a part of the image. We are taking part of the image and perform discrete cosine transformation. Using this discrete cosine transformation, we are gather the most important pixels in the left top corner of the image. Then for the selected block, and semi or middle important part we are placing in the middle of this of the block, right? Then the least important part will be gathered into right bottom corner of the image, right? I will show you how to apply DCT or discrete cosine transformation algorithm on using an example, right? Uh, Then we can perform forward discrete cosine transformation. Before going to the forward discrete cosine transformation, I will show you an example about the DCT. In DCT, we are divide our image into 8 by 8 sub images, right? 8 by 8 sub images means 64 pixels. We are taking 64 pixels separately as a 8 by 8 block. Then we are changing the pixel values in between 128 to 127, in between 102 minus 128 to 127. Okay, let's take an example. Okay, this applying DCT is very simple. Let's see this example, right? Then you can clearly understand what are we going to talk about, right? This is the image, original image, right? This is the original image, right? This image has a set of pixels, right? Pixel by pixel. Let's say this is 64 by 64 image, right? Then we are taking a sub image from this. In standard way, we are taking 8 by 8, totally 64 bit. Just forget this number, right? Just we are taking 8 by 8 or totally 64 pixel part or sub image from this original image, right? We are taking this part separately. For this example, uh, 64 bits. It means 64 pixels. Then I have to calculate the calculation 64 times. Therefore, it is very time consuming. Therefore, just only for this example, I'm taking a block with 4 by 4 size 4 by 4, right? In standard way, we have to take 8 by 8, but for this example, I will take 4 by 4 one, right? 4 by 4, totally 16 pixels, right? This is just only for this example, right? In real world case, we have to take 64 pixels. Okay, then I will put some random numbers here. Let's say 111, just some random numbers, right? 236, 255, 200, 96, 114, 125, 124, 123, 148, 150, 50, and say 60, 160, right? Then we are performing DCT, discrete cosine transformation, or in other words, we are changing this pixel values in between minus 128 to 127. Simply, we are reducing this pixel value one by 128. It's very simple, right? Can I take this one again? Right? Now we are taking pixel by pixel and reduce the amount, the value from 128, right? 111 minus 128 means 16, no, 70, right? Minus 70. 146 minus 128, 12. And so on, we can calculate the difference. So we can reduce the pixel values by 128. 154 minus 128, 26. Then 192 minus 128, 64. 255 minus 128, 127. 200 minus 128, 72. 96 minus 128, minus 32. 192 minus 128, 64. Yeah, 64. 236 minus 128, 108. Right? Then 114 minus 128, minus 14. 125 minus 128, minus 3. Then this is minus 4. This is minus 5. This is 20. This is 150 minus 128, 22. 50 minus 128, minus 78. Then 160 minus 128, 32. Right? Now we are changing the numbers, these pixel values, by reducing 1 to 8 from each and every pixel. Then we are come up with this result. Right? This is the result after discrete cosine transformation. After we can take this first pixel, 0, 0 index pixel. We called it as DC component. DC component. We called it other pixels as AC component. Right? DC component and AC component. The result is after performing DC quantization or discrete cosine transformation. Right? We are taking, we are applying DCT and we are come up with the 64 coefficients. In first one, or the zeroth indexed coefficient, we call it as DC component, and another 63 pixels we call it as AC components, right? Then we can apply forward discrete transformation, right? Actually, we are changing the pixel values to a spectral information or the intensity values, right? We can apply forward discrete transformation, the first equation for this one. For this result, one by one, by taking row wise and column wise, we are applying this equation, right? This equation we can apply row wise and column wise. In this course, we are not taking this equation to calculate the values, right? We are taking the DCT image, right? DCT image and apply the previous equation in row wise and column wise, and finally we have come up with this result, right? Okay. We are not mainly talk about this equation, right? This is a bit complicated. After these two steps, we have come up with these types of result. First, this is we have original image. I told you earlier, we are taking 8 by 8 block in real world case, but in this case, we are taking for the example, I am taking 4 by 4 block, right? Then this is the shifted block, or in other words, we are reducing this number by 128, and we have come up with this set of numbers. This set of numbers should be in between -28 to 127. Then we are applying forward discrete cosine transformation of this equation, uh, row wise and column wise. Then we can come up with this result. This is the result we are getting uh, after performing FDCT algorithms, right? Then we are performing further process on top of this one, FDCT, right? Okay, then we are performing quantization. In quantization, there are two types of quantization. First one is uniform quantization. Second one is non-uniform quantization. Uniform quantization means we are taking, or we initialize a quantization factor, a number, right? Or in non-uniform quantization, we are using this type of table, right, for the quantization process, right? For the Luma part, we are using this is the default quantization table for the Luma part, and this is the default quantization table for Chroma part. When you get a question based on this quantization, you will get this table, right? Therefore, no need to remember this number. Definitely, will get this table in your paper, right? First, just try to do non-uniform quantization with an example, right? This is very simple. We are dividing the pixel value with the quantization factor. Then we are round up this amount to the unit, nearest unit, right? We are dividing pixel value with the initialized quantization factor, and the number, sometimes the number which is having decimal numbers, sometimes it might be have a decimal numbers, then we are round up these numbers to nearest least digital sorry, nearest first digit, right? Okay, I will show you an example with this one. Let's say after applying uh, forward cosine transformation, let's say we are come up with a set of pixels with these values, right? We are not performing the forward quantization here, right? Just assume after applying forward discrete cosine transformation for this result, and we have get this answer for an example, right? Let's say we are applying FCDT here, so FDCT here, then we are come up with this set of values. Let's say this is 515, then this is 65, then -12, then 4. This is again the set of random numbers, right? For this example, 3, 2, 6, -12, 6, 11, -1, -8, 3, -4, and 2. This is the result after applying FDCT, just assume, right? Then I will take non-uniform quantization. Therefore, I have to consider the quantization table as well. This is the standard quantization table for Luma and Chroma, right? This is the default quantization table for Luma. This is the quantization table for Chroma, right? But in this case, I'm using another random numbers, right? In other words, it will take, otherwise it will take too much time, right? Just assume this is the quantization table used for this quantization algorithm, right? Let's say 16, 11, 10, 16, 12, 12, 14, 19, 14, 6, 13, 16, 24, 14, 17, 32, and 20. Actually, here we are, what we do is we are dividing this number pixel by pixel. We are taking 515 and divided by 16. What is the number? 515 divided by 16. It is 32.18, right? 32.18. Then when you round up to the nearest least digit, right? Then the result will be 32. If you get a number greater than or equal to 5, we are adding a number to this one. Let's say this is 32.54 something. This value should be 33, right? 32.67 again 33. 32.1, the result will be 32, right? We are round up to the least complete number, right? Okay. I'll take the result in this block, into this block. Four, 3, 4, 3, 4. When you divide 15 by 515 by 16, it will give 32. 65 by 11, 6. Minus 12 by 10, minus 1. 4 divided by 16, definitely 0. Minus 12 divided by 12, minus 1. 3 divided by 12, 0. 2 divided by 14, again 0. 6 divided by 19, again 0. Minus 12 divided by 14, minus 1. 6 divided by 13, again 0, I think. 11 divided by 16, 1. Minus 1 divided by 24, again 0. Minus 8 divided by 14, minus 1. 3 divided by 17, 0. Minus 4 divided by 32, again 0. 2 divided by 28, again 0. Right? This is the result of applying quantization. Right? Actually, here what we are doing is we are gather the very useful information in the left top corner of the image. See, left top corner of the image, and we are gather the least important image at the left right bottom corner of the image, and we are placing the middle important image in the middle of the image, right? Then we here we are come up with the number of zeros, right? Then the zeros is very easy to compress, right? Actually, what we are doing here is an image is again a set of numbers. We are taking some space from the storage devices to store these numbers, right? If we reduce the number of pixels, right? If you reduce the number of pixels, then our image will be definitely getting a little less amount of space, right, from the RAM, right? This is the purpose of converting this too much numbers to this type of zeros and nearly zeros, 1 and 0 values, right? This is a very important part. We call this as DC part. We call this rest as AC part. AC component and DC component, right? Okay. See, this is another example, right? First, we have the original image. Then this is the result of after adding forward discrete cosine transformation. First, DCT transform and another next forward discrete transformation. In this case, we are using a uniform quantization. Uniform quantization means first we initialize the quantization factor, right? In here, this example, the quantization factor is 60. Then we are dividing all of these 64 values by 60. In this case, we used non-uniform quantization factor, or we used a quantization table. We have set of different numbers in this table. Then we are taking the respective relevant pixel from the image and divide this image or pixel value by this respective quantization factor, the value from quantization table, right? But in this case, we are initializing a quantization factor first, right? We are initializing a quantization factor first. Then we are dividing all of these 64 values by 60. Then we can come up with this result, right? This is the quantized image for this value, right? Quantized 64 pixels for this one. See, previously it had too many numbers, right? This image will take too much space from our storage device. But in this case, this image is converted to completely zeros. Then we can it is really easy to compress zeros if compared to this type of numbers, right? Then we have to perform zigzag scan. You have to remember this style, right? When you convert or when you apply zigzag scan, we have to remember this pattern. First move to right side, then go to diagonal, then go down, then go to diagonal in upward direction, then again go to right side, down, or the diagonal direction, then go to down, then go by another row in the diagonal direction, and so on, right? The purpose of this zigzag scan is first we have a 8 by 8 matrix. After performing zigzag scan, we are converting this 8 by 8 matrix into 1 by 64 vector or 1D matrix, right? 1D matrix. We are converting this 2D vector, 2D matrix to a 1D vector, right? 1 into 64 because we are taking 64 bit, 64 pixels in real world case. Then we are come up with 1 into 64 different values with the 1 into 64 vector. But in our case, we are only just taking 16 pixels, right? This is 4 by 4. Then we are come up with the 1 into 16 vector, right? Let me show you how to calculate or how to perform. So, how to perform zigzag searching algorithm on this result, right? First, starting with the first point, 0, 0 point, right? First, starting with this point, then we can place 32 here. 32 after moving right side 6, then come down with the diagonal direction -1, then go down -1, then go up in diagonal direction 0 and -1. Then go to right side 0, come down in diagonal direction 0, 0, -1, 0, 0, -1, right? Then go to this side in 0, go up in diagonal direction 1, 0, then go down 0, finally come up with this number. Right? You have to remember this pattern, right? This we call zigzag pattern, right? Then finally we have come up with a vector with size 1 into 16. This result will be taken by using by applying zigzag stretching algorithm, right? We are converting the 2D matrix into 1 into 16 vector, right? Right, this is the example given in the slides. See, 26, go this direction, -3, 0, then go down, -3, -2, -6, 2, -4, 1, then -3, then go down 1, and so on. Then finally, we are ending with this number, right? Then we can get a sequence of these numbers. We call this as 1 into 64 vector, right? This is zigzag scan. After finding the zigzag or the vector, we are applying according to this pipeline, we are applying 2 algorithms, right? This DPCM and runner length encoding, right? DPCM algorithm is used for DC factor. RLC algorithm is applied for AC factor. What is DC and AC factor? What is the DC and AC factor? We call this the very first pixel as DC. The remaining is AC. We are applying. We are applying differential pulse code modulation (DPCM), right, into DC factor, then the runner length encoding for AC factor, right? Let's see how we can apply these 2 algorithms for this example, right? Okay. Finally, if we apply the zigzag scan algorithm for all of these blocks, all of this block means for this example we are taking just only one, right? We can calculate 8 by 8 blocks for the entire image, right? Something like this. We are dividing our image with 8 by 8 blocks, then we can come up with a set of these vectors, right? Then we are considering the first element of this vector. We called it as DC factor, DC component. This one is a DC component. Then DPCM algorithm we are applying for this DC factor. We are reducing this number from the next one. First, we are taking 45 and we are placing 45 as the first element for after adding DPCM algorithm. Then after taking 54, we are reducing 54 by 44. We are reducing or subtract 54 by 44. Then the difference in between this one is 9, right? We are placing 9 as the BC factor for second vector, right? Then after taking this one, 48. 48 minus 54, it means minus 6. We are taking the DC component for the third vector as minus 6. And so on, we are applying the same steps for the entire set of vectors. And finally, 32 and 36, we are reducing 30. This one is made some error, I think, right? Yes. Oh, no, it's correct, right? We are reducing 36 by 32. 36 by 32, subtract 36 by 32, then 4. The result for the DC factor for the final vector is 4, right? This 12 is taken from some value in up direction, right? Let's say this one, the previous one for this vector is DC component of the previous vector is 20. Then we are reducing or subtract 32 by 20. Then we can come up with the 12, right? Then finally, for the final vector, we are subtract 32 by 36 by 32. Then we are come up with the DC value 4 for the final vector, right? After applying DPCM to the DC component of this vector, then we can come up with these numbers, right? We are reducing the next value from the previous value. 45 minus, sorry, 54 minus 45, 9. 48 minus 54 minus 6, and so on. Then 36 minus 32, 4, right? We have come up with this number after adding DPCM algorithm for DC component. Then AC component. We are applying runner length encoding for AC component, right? It is bit different. Then I will show you the example, right? Okay, these are the result after we getting after we applying zigzag scan algorithm for this result, right? Now we are going to apply runner length encoding for this one. Runner length encoding, right? This runner length encoding has 3 parts. First one is the runner length, then size, then amplitude, right? I'll show you what are those things. As the first element, first part of the runner length encoding is the number of leading zeros, right? The number of leading zeros. We call it as runner length, right? Runner length. Number of leading zeros, then number of bits required to represent the AC component. Number of bits required to represent actual value for the AC component. AC component. Right? This is the first part. As the second part, we are taking the amplitude or the actual value. Right? This is the runner length algorithm. First, number of leading pixels. So number of leading zeros. Then number of bits required to represent the AC component. Then actual value. Okay. Then I will show you the result after performing runner length encoding for this result, right? First, we are considering 36 because this one will be taken as the DC component. Then we are performing the runner length encoding for AC component. then we have to consider 6, right? How many zeros are in front of this 6? No, right? Then we are adding 0 here. Then when you convert this 6 into binary form, how many bits are need to represent this 6? If you convert this one into binary form, this 6 will be represented by 110. 110. Then how many bits required for this 6 is 3, right? Then number of bits required to represent the AC component is 3. Then close the bracket, then open another bracket. Actual value is 6, right? This is the runner length encoding for first character, for the first number. Okay, then take the second one. We are adding a semicolon here, right? Then how many zeros are there in front of -1? Again, 0. How many bits are required to represent this number? This is -1, again, 1 bit. Then the actual number is -1. This one is done, this one is done. This -1 again. How many zeros are there in front of this -1? Again, 0. Now number of bits required for this -1, 1. Actual number is again -1. Semicolon. Then we are skipping this 0, right? Then go to this one. For how many zeros are available in front of this -1? 1, right? Then we are adding 1 here. How many pixels are need for represent this number? 1 pixel, so 1 bit, not pixel, right? Bits. Then what is the actual number? -1. This one is done. Then we are skipping this one, and this one, right? Then we have come up. We have to apply runner length encoding for this character, this number, right? How many zeros are there in front of this -1? 1, 2, 3. We are adding 3 here. How many bits are required to represent this number? 1. What is the actual number? -1. Right? Then this one is done. We are skipping this one. Then for this one, how many zeros are in front of this one? 0. Sorry, 1. How many bits are need to represent this number? Again, 1. What is the actual value? 1. Semicolon. After entire numbers are zeros, then we are applying 0, 0 at the final, right? This is the result after taking or after performing runner length encoding for this AC component. It is very easy, right? When you understand in proper way, it is very easy. We are finding or we are counting the number of leading zeros are there in front of the target number. If it is no, if there is no any zeros in front of this 6, then we are adding 0 here. Then as the second parameter, we are finding the number of bits required to represent the AC component. In this case, 6. 6 is represented by in binary form 110. Then we need 3 bits. Then we are adding 3 here. The actual number is 6. And so on, we can get the result by adding runner length encoding for this result. Right. Right, this is the result for the given example in the slides, right? -26. So we are skipping 26 because this one is the DC component. The AC component is starting from this point onwards, right? Then -3. Then how many zeros are there in front of -3? 0. Then putting 0 here. Then how many bits required to represent this -3? -3 we can represent by using 1, 1. Then 2 bits required. Then adding 2 here. Then the actual number is -3. Semicolon. For the second one, is it 0? Then we are skipping this one. Then -3 again. How many zeros are there in front of this -3? 1, 0. Then adding 1 here. -3 we can represent -3 in using 2 bits, then we are adding 2 here, then the actual number is -3. And so on. Let's say take another example. -2. How many zeros are there in front of this? 0. No any zeros in front of -2. Then put in 0 here. How many bits required to represent this number? Here we can represent -2 in binary form by using 2 bits. 1, 0. Then 2 here. Then the actual number is -2. And so on. We can apply runner length encoding for entire set of numbers or entire this vector. Then after this point onwards, we are not having any zeros, sorry, any number here except 0. Then finally we are adding 0, 0, right? This is the result after applying runner length encoding for this vector, right? I will share these slides with you, then you can go into this one again after. Okay, then we are adding Huffman coding. Huffman encoding is another algorithm. We are not going to talk about the Huffman coding. If you are interested about about this step, you can go you can understand or you can learn this by just Googling, right? Huffman encoding is mainly used for radius or compression, or it may this might be used to change or reduce the number of zeros, right? We are not talk about the Huffman encoding here. Okay, then after applying Huffman encoding, we are finally come up with the compressed JPEG image, right? Then let's see one by one step again for a complete example. Initially, we have an original image with different pixel values. Then we are shifting these values in between -28 to 127, right? In between -128 to 127 by reducing this pixel value by 1 to 8, right? Then we are finally come up with this result. Then after adding forward discrete cosine transformation, we can come up with this result. We are applying forward discrete cosine transformation on top of this result, right? We are not going to talk about in detail about the forward discrete cosine transformation. We are applying the previously showed algorithm here. Then we are come up with this result. Then quantization. For the quantization, there are two types of quantizations. Uniform quantization and non-uniform quantization. When we choose uniform quantization, first of all, we have to initialize the quantization factor. It is a number. Then we are dividing all of these pixel values by the selected number and round up the amount and place the relevant place. In non-uniform quantization, non-uniform quantization, we are using a quantization table, right? I have showed you two default quantization table for luma factor and chroma factor. We are taking this table and considering the relevant pixel one by one and divide the respective pixel value from the pixel value from quantization table, and again round up the amount, the value, and place the respective place in the result, right? After performing the quantization, we are come up with a bunch of zeros, right? Then we are performing zigzag scan, right? Zigzag scan. The first element we called the first element of this one is we call DC factor. Another rest of elements, 63 elements we are considering as the AC factor, right? We are performing a specific pattern. Go right, go down in diagonal direction, go down, then go up in again diagonal direction, go left, so go right, go down, and so on. After finding this vector, the purpose of zigzag scan is we are converting this 2D matrix to 1D vector, right? Finally, we are come up with the 1 into 64 vector. After that, we are applying runner length encoding for AC not for DC part. We are applying runner length encoding for AC part. We are applying what we called DPCA, right? Differential pulse code modulation for DC factor, right? After adding runner length coding for this one, we are come up with this result. After this result, we can apply Huffman coding for this one, right? This is the complete uh, process of encoding part. Then once you encode this one, we are not considering this is the image, right? We are changing so many things to the image. Then we have to decode, we have to reverse these steps, right? Finally, then after this adding Huffman coding, we are encoding. We are encoded the image. We cannot see the actual image here, right? Then we have to perform the reverse cycle, reverse steps to get the uh, real image or the real uh, compressed image. Then as the first step, we are decoding or reverse, we are applying reverse of the Huffman and Ranelagh encode. After dequantize, or first we divide by the quantization factor. In this case, we are multiply using the quantization factor. Then apply inverse discrete cosine transformation. Inverse. See this equation, right? This is for forward discrete cosine transformation. This one is inverse discrete cosine transformation. All right. Once you have performed the compression by using Huffman coding, after that you have to do the reverse step, right? To perform the reverse step, you have to add inverse discrete cosine transformation. After, as the final step, we are adding 1 to 8, because as the first step we are convert the numbers in between 1 to 8 to minus 1 to 8 to 1 to 7 as the first step, right? Then in this case we are converting again these numbers by adding 1 to 8, right? Finally, we are come up with the encoded or the compressed image, right? This is the complete journey of this compression. First, we have original image. Then we are applying DCT transformation and forward discrete cosine transformation. Then we can come up with this result. After come up with this result, we are applying quantization. We can use two different ways to do quantization: uniform quantization and non-uniform quantization. After getting the quantization, we are applying after applying we are applying after getting the quantization, we are applying two algorithms, right? Two algorithms, or sorry, zigzag scan algorithm, right? Then we are come up with the 1D vector, right? 1D to 64 vector. Then after that we are applying DPCM algorithm for the DC factor, tunnel length encoding for the AC factor, right? In this case, I'm not showing these two steps, right? After adding the runner length encoding, we are applying Huffman coding, and we can come up with the compressed one. After, we have to perform the reverse engine, reverse steps, right? Then dequantization. The result of the dequantization is something like this. After decoding or adding 1 to 8 here, right? Decoding and finally come up with this result, right? This is the final result of the image after compression, right? But see, when you see the pixel by pixel, this is the first pixel of the original image. This is the first pixel of the compressed image. Initially, it is the value of this first pixel is 200, but now 199. If we take the difference in between this, we can come up with this result. We call this one as the errors. Errors. Yeah. If we not doing any errors in the during the compression, the entire this metric should be 0. But in this case, That is not 0, right? We have come up with some zeros with minus value and plus values. It means we are when we performing the compression, definitely there should be some errors, right? That is why we called JPEG is a loss compression file type. Loss compression file type. We are changing some information about the image, right? We are changing the information. Previously, the first pixel value is 200, but now the pixel value is 199. Previously, the last pixel 186, but now it is 184. We are changing the information details of the image, right? That is why we call JPEG is a loss file type. When we compress or perform the compression on the JPEG, finally we have come up with the answer or the result with some loss information, right? We call this matrix as the errors, right? Decoded and encoded errors, right? This is the complete cycle of uh, encoding, JPEG compression, not encoding, right? JPEG compression, right? Let's summarize these steps. We can apply these steps for the video compression as well, right? Once you find out the uh, uh, matching pixels in video, when you find out the matching pixels by considering the set of frames, right? Then we can apply these steps for more compression, right? Let's summarize these steps. First, we are changing the color space, uh, converting to RGB to converting RGB color space to uh, YUVO This is the first step. Then we can perform the downsampling, right? I have showed you in this slide downsampling or subsampling, right? Plus subsampling. Then we are adding the shifting process or DCT. Then we are come up with the shifted one, right? After adding DCT, right? After we have to add forward discrete cosine transformation, right? Then we are come up with a result. Then we can perform the quantization. There are two types of quantization. First one is uniform quantization. Another one is non-uniform quantization, right? If you use uniform quantization, we are using a quantization value, quantization factor. In non-uniform quantization, we are using a quantization table, right? In this case, we are using quantization factor. For this one, we are using quantization table, right? After this one, we are performing zigzag scan. After performing zigzag scan, we are come up with the 1 into 64 vector, right? 1 into 64 vector. Then we have two components, DC component and AC component. After that, we are applying DPCM algorithm for DC part. We are adding runner length encoding for AC part. Then after we are feeding the entire result to the Huffman code, right? Then after that, we are applying the reverse steps for getting the actual image after compression. This is the complete path of JPEG image compression.